All right, part 3, the final part. In the first part, we did the life cycle of red dwarfs. In the second part, we did the life cycle of low-mass stars. Now we're going to finish up with the life cycle of high-mass stars. Now, just like the other ones, again, the high-mass star life cycle starts with the protostar stage and then the main sequence stage, where you are fusing hydrogen in the core. The only difference, again, is that the high-mass stars take even less time to go through these stages because of the added pressure from the gravity. Now, here we go. During the main sequence, just like on every other star, a high-mass star is going to be fusing hydrogen. And just like every other star, the main sequence will end when the hydrogen in the core runs out. Now, after the main sequence, a high-mass star is going to be able to fuse way more things than the low-mass stars could. And that's because a high-mass star with its extra gravity is able to squeeze its core tighter and therefore produce higher temperatures inside the core, so they can fuse bigger and bigger elements. Now remember, you need a higher and higher temperature to fuse bigger and bigger elements because it's harder and harder to fuse an element the more protons it has in its nucleus. Now, on this chart I'm about to show you, I'm going to show you the other things that can fuse in a high-mass star. I am not going to draw little F's on any of my diagrams to show what's fusing because everything that I draw in these diagrams is fusing unless I otherwise say. So during the main sequence, again, hydrogen fusing in the core, so the core would just be drawn like this. That's just the core, not the whole star we're drawing here. I'm only drawing the core. So the core has hydrogen fusing. Now, after hydrogen fuses, when it runs out, fusion turns off for a moment and the core shrinks and makes the core temperature go up until the point where helium can fuse next. So the helium fusing starts the next stage, whose name I will write up here in just a second. So after the main sequence, the first thing that fuses is helium. Now, just like in the low-mass star, when that's happening, we're going to have a shell around the core where hydrogen is fusing. And that's because the higher temperature in the core makes the area around the core much hotter as well, to the point where the hydrogen can fuse there too. Now, it's not the entire star that's fusing here, just the core and a small shell around the core. So helium fusion, hydrogen fusion. The helium will fuse until it runs out, and the thing you make out of helium is a bunch of carbon and oxygen. So the next thing that will fuse after helium is carbon. When the helium runs out, the core shrinks, gets hotter until the carbon can fuse. When the carbon is fusing, because the core is hotter, you gain an extra shell. Every time a fusion turns off in the core, you gain a shell for it in the next part of the stage. So here, when carbon is fusing, we have a shell for hydrogen and helium around it. Just notice that this is the same order that things fused as the star went through its life. Now, when the carbon runs out, the core is going to shrink and get hotter until you could fuse something else. Now, notice I'm not telling you exactly what we make out of carbon, because when we fuse carbon, we make a whole bunch of other things. And one of those things is the next thing that will fuse, and that's neon. So if we're looking so far in this stage, we've fused helium, and then carbon, and then neon. Now, when we start to fuse neon in the core, now notice I've got neon in the middle, and I've got a new carbon shell from the last fusion, in addition to the helium shell and the hydrogen shell that we've had all along. Now, the neon will fuse until it runs out. When it runs out, the core will shrink, it will get hotter until we can fuse oxygen. The oxygen will fuse until it runs out. Then the next thing that will fuse will be silicon. So when we're fusing all of these things, when we're fusing silicon, we have a shell for every one of these other things all at the same time. That means we're fusing a lot of things at once during this stage. So that means our luminosity is going to go way up. And if the luminosity goes way up, it's going to push the rest of the star outward way more than ever before. And that means that this type of star will get extremely big after the main sequence. And that's why we call this stage the Supergiant Stage. So the stage after the main sequence in which a high mass star fuses a whole lot of different things is called the Supergiant Stage. So I'm going to write that down up here. Give me just a second to pop this pin open. Here we go. So supergiant. Okay. Supergiant stage. So during the main sequence, we fused hydrogen. And then after that, during the supergiant phase, we fused these things in order. So make sure you know this order. Now, when the silicon is done fusing, it produces iron. So the symbol for iron, unfortunately, is Fe, but I'll write iron down next to it. Iron. And when that happens, the star is no longer a supergiant. When the core runs out of silicon and makes iron, the supergiant stage is over. And that's because a core made of iron is a giant problem for the star. And the reason for that has to do with the periodic table. Now, it turns out that all of these other elements that we've drawn here, all of these other elements are smaller than iron. They're smaller than iron. And if you fuse hydrogen, remember we said that you get light out. That's a form of energy coming out. The same thing is true for helium. You get light out. For carbon, you get light out. Neon, you get light out. Oxygen, silicon, you get light out. For any element that's smaller than iron, when you fuse it, you get energy out. For anything iron or bigger, you actually have to put energy in to get it to fuse. However, fusion was the energy source in a star. So this core is not going to fuse. It needs energy to fuse, but fusion is where a star's energy comes from. So you can't power your fusion with the fusion. That doesn't make sense. You can't power your car with your car. That doesn't make sense. So as soon as the core becomes iron, it will never be able to fuse that iron, no matter how hot it gets its core. So no matter how big the star is, iron is the end of the road. Now, that means that the core of the star at this point will not be able to fuse. Just as an aside, at this point, the supergiant will be as big as it possibly can be. And when I say as big as it can possibly be, some of these supergiants will actually be bigger than the orbit of Neptune, the farthest planet from the sun. These stars are bigger essentially than the planet part of our solar system. Giant, 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 giant. That's why it's supergiant. Now, back to the iron. When that core becomes iron, it can't fuse it. So what does gravity do? Well, it crushes the iron. It crushes the core of the star. And if that happens, if we look over here, if this core suddenly crushes, it'll crush so quickly that the material will rebound off of itself and then ricochet back out through the star. That's not good for a star. If this material ricochets back outward, it's going to literally explode the rest of the star. So most of the star is going to explode off in what we call a supernova. So right at the end of the supergiant stage, in about 10 seconds, a supernova happens. Now, what does a supernova look like? Well, your book has a couple of pictures of them. So here we go. So if you look right here, back in 1987, September of 1987, was the first time that we predicted accurately that when a star was going to explode, which was a big indication that we were right about this whole process, the whole life cycle of these stars. So we predicted that that star that the arrow is pointing to would explode. And right when we thought it would, it produced a giant flash of light, as you can see in this picture. Now that slowly faded, and you can't see it anymore today, but supernova are insane explosions. If our sun could supernova, but remember, it can't because we're not a high mass star, but if it did, if our sun supernovaed, or if our sun died in a supernova, then you would receive more explosive force on your body than if you took an average atomic bomb, pressed it to your face, and then blew it up. That atomic bomb explosion in your face would be less of an explosion than the sun going supernova 93 million miles away. That is how big a supernova is. And that's our sun. Our sun's small. It's too small to supernova. The stars that do go supernova would be an even bigger explosion. Now, the star doesn't just disappear. Most of the material of the star explodes off. All of these shells would explode off, and then everything else that's around the star would explode off. And what you're going to be left with is basically a giant cloud of gas that is shot out of the supernova. It's known as a supernova remnant. Supernova remnant. All right. After that star explodes, what's left behind is the leftover core that was originally made of iron. Now, that leftover core can become one of two things depending on how much material is left. The first thing it can become is called a neutron star, if less than 2 or 3 solar masses is left. The other thing it can become is a black hole, if more than 2 or 3 solar masses is left over. We'll talk about neutron stars and black holes in class. So this is the complete life cycle for high mass stars. All right. Now, a couple of things to note. This supernova takes much less time to kill the star than the planetary nebula did for low mass stars. A supernova takes about 10 seconds to happen, even though the actual cloud that shoots out of the star can remain visible for thousands of years. A planetary nebula, however, on a low-mass star, when it slowly puffs itself to death, can take thousands of years to destroy the star in the first place. So it's a much gentler process. Supernovas are not gentle at all. Now, the final thing I want to say about supernovas is something that's a little bit ironic. Now remember, the whole reason that the supernova happened is because iron has to have an energy source in it to fuse, and the star didn't have an energy source. Well, if the star explodes, an explosion is a source of energy. So as soon as the star explodes, the iron now has an energy source. And so just for the 10 seconds that the star is exploding, iron will fuse. Now, what do you make when you fuse iron? You make a lot of things, but here are I'll just tell you some examples. Some things you make when you explode iron are gold, silver, platinum, and uranium. You may notice that those are all expensive, rare things. And the reason they're expensive and rare is because they're only made when a star explodes. So every piece of gold and silver and platinum that you've ever seen or touched or maybe are wearing right now and also some's in your computer or phone at this second, that stuff shot out of an exploding star at some point, which is crazy. All right, that's the end of this video series. Remember, we'll talk about the dead stars, white dwarfs, neutron stars, and black holes when we get back to class at the beginning of next week. Sorry for the quality of the videos. I was unable to find anybody to film them for me, so it's okay. All right, see you guys next week.